Two galaxies are locked in a slow, beautiful dance of destruction. Their spiral arms are pulled into long, glowing streamers of stars, a preview of a merger that will forge a single, new galaxy. This is not an anomaly. It is the story of our cosmos. The universe you see, from the planets under your feet to the stars above your head, was built by violence. Today, we are going to witness 25 of the most massive cosmic collisions that literally shaped everything. You will understand how gold in a ring and the moon in our sky are products of ancient, unimaginable violence. We will see how a single asteroid strike rewrote life on Earth, and how a collision we cannot even see proved the existence of dark matter. What is the most surprising thing you think a cosmic collision can create? Our story begins with a bang, but not the kind you might think. The very first entry on our list is the origin of all cosmic violence. It is the Big Bang. Calling it a collision stretches the word to its absolute limit. There was no space for things to smash into each other, and there was no time for a before and after. Instead, picture a single point of pure potential, a singularity of infinite density and temperature. This was not an object floating in a void. It was all of existence, every single ounce of matter and energy, compressed into a space smaller than an atom. Then it happened. This point of everything did not explode into empty space. It unfurled. Space itself began stretching, and time began ticking. In that first unimaginable moment, the universe was born in a fireball of pure energy, a cosmic forge so hot and dense that the fundamental forces of nature were forged within it. This was the ultimate collision, a collision of energy and potential giving birth to reality. From that searing, expanding cloud of particles, the first seeds of structure were sown. Tiny ripples in density, like waves on a primordial ocean, were the blueprints for everything to come. Every galaxy cluster, every spiral nebula, every star that would ever shine, and every planet that would ever form, all trace their lineage back to those first chaotic moments. Without this foundational event, this violent birth of space and time, there would be no canvas for the epic collisions that were to follow. The stage was set, and the actors were just beginning to form. From that searing, expanding cloud of particles, the universe entered a long, silent night. For millions of years, there was only darkness. The cosmos was a featureless fog of hydrogen and helium gas, still glowing faintly from the heat of its birth, but with no light to pierce the gloom. Then, something began to stir in the dark. This brings us to our second massive cosmic collision, the event that ended the cosmic dark ages and lit the first fires in the universe. It was the formation of the very first stars. These were not stars like our friendly, stable sun. They were monsters, and their birth required a delicate, violent dance. Remember those tiny ripples in density from the Big Bang. Over eons, gravity began to work on them. Slightly denser patches of dark matter, that mysterious invisible stuff that makes up most of the universe's mass, began to attract one another. They gently collided and merged, forming growing halos, invisible gravitational wells. Into these wells, the primordial hydrogen and helium gas began to flow. Think of it like water finding the lowest point in a landscape. Vast clouds of gas, drawn by the gravity of the dark matter, slammed together. These were not head-on crashes, but immense, chaotic mergers. As the gas clouds collided, they compressed. They grew hotter and denser. For the first time since the beginning, pockets of the universe became so incredibly dense and hot that nuclear fusion ignited in their cores. A star was born. But these first stars, known to astronomers as population 3 stars, were unlike anything we see today, with only the pure, simple elements of hydrogen and helium to feed on. They grew to staggering sizes, hundreds of times more massive than our sun. They burned with a ferocious blue-white intensity, and they lived fast and died young. Their formation was the universe's first crucial step from smooth, boring emptiness to glorious, structured complexity. It was a collision of gas on a cosmic scale, triggered by the unseen hand of dark matter, and their brief, brilliant lives would set the stage for everything that came next, because their deaths would be even more violent and transformative than their births. Those first monstrous stars did not fade quietly into the cosmic night. They lived for only a few million years, a blink in cosmic time, before their own immense gravity turned against them. Their deaths were the third and fourth entries on our list. Events of such staggering violence they transformed the very chemistry of the universe. First came the supernova. A star hundreds of times the mass of our sun burns through its nuclear fuel at a frantic pace. When the fuel runs out, the outward pressure from fusion suddenly stops. The core collapses catastrophically in less than a second. Then it rebounds. The outer layers of the star are hit with a shockwave of unimaginable power, exploding outward in a supernova blast so bright it can outshine an entire galaxy. This is where the universe got its first heavy elements. In that incredible forge of heat and pressure, atoms were smashed together to form carbon, oxygen, silicon, and iron. These supernovae were the universe's first factories, scattering the seeds of future planets and life across the cosmos. But for the very largest of these first stars, their death was even more extreme. This brings us to collision number 4, the birth of the first black holes. If the collapsing core was massive enough, perhaps over 40 times the mass of our sun, the rebound never happened. The collapse did not stop. It continued, crushing matter into a point of infinite density as singularity. The fabric of space-time itself was punctured, creating a black hole. This was a collision of a star with its own inevitable fate. A gravitational victory so complete it created an object from which not even light could escape. These first black holes, the stellar mass remnants of the first stars, sank to the centers of the young galaxies beginning to form. They were the quiet, dark seeds of future giants, waiting to feast. But our story now turns from the death of stars to the birth of our own home, because the next collision is the one that made Earth, and you, possible. It is the most important crash in our planet's history. The seeds of life were forged in the violent deaths of stars, but how did those seeds find their way to a young, molten Earth? The answer lies in a period of relentless chaos known as the Late Heavy Bombardment. Roughly 4 billion years ago, the inner solar system was not the orderly place we see today. It was a cosmic shooting gallery. The formation of the giant planets like Jupiter had stirred up the debris left over from planetary construction, flinging countless asteroids and comets inward. For hundreds of millions of years, these leftover planetesimals rained down on the young worlds. You can still see the evidence. Look up at the full moon on a clear night. Those dark, smooth patches you see, the lunar maria, are not oceans. They are immense plains of hardened lava that welled up from catastrophic impacts, permanent scars from this violent epoch. The entire surface of Mercury is similarly cratered, a testament to the pummeling it endured. Mars bears the marks as well, and Earth, being the largest target, would have been hit the hardest. But here is the incredible twist. This period of destruction may have been absolutely essential for creation. Those icy comets and water-rich asteroids were not just projectiles. They were delivery vehicles. With every colossal impact, they brought precious gifts: water, the very essence of oceans, and complex organic molecules, the chemical building blocks of life. The violence that scarred our world also may have seeded it with the fundamental ingredients for biology. So the next time you take a drink of water, consider its epic journey. It likely arrived on a ball of ice and rock, screaming through the primordial atmosphere in a fireball, in a cataclysm that helped make our living world possible. This bombardment shaped the very geology of the planets, but one collision stood out for its sheer, transformative scale. It created our constant companion in the sky and set Earth on a unique evolutionary path. The scar from that ancient bombardment still circles our world in the form of the moon, but another impact would one day rewrite the story of life itself. This is collision number 5, the Chicxulub impactor. 66 million years ago, a rock from space, roughly 10 kilometers wide, ended a geological era. It was not just an asteroid. It was a planet killer. Traveling at over 70,000 kilometers per hour, it punched through Earth's atmosphere in an instant, striking the shallow seas of what is now the Yucatan Peninsula. The energy released was equivalent to billions of atomic bombs detonating at once. The immediate aftermath was a vision of pure hell. At the point of impact, the rock and a vast volume of the Earth's crust were vaporized, blasted upward in a plume of superheated plasma. The shockwave ignited continent-wide firestorms. Seismic waves, thousands of times more powerful than any earthquake in recorded history, rattled the entire planet. In the nearby ocean, the displacement of water sent a mega tsunami, a wall of water over a kilometer high, racing across the Gulf of Mexico. But the true killer was what came next. The impact ejected trillions of tons of vaporized rock, dust, and sulfur aerosols high into the atmosphere, encircling the globe. Sunlight vanished. For months, possibly years, the world was plunged into a deep, cold twilight known as an impact winter. Photosynthesis ground to a halt. Plants died, herbivores starved, and then the carnivores followed. The food chain collapsed. In this prolonged darkness, 75% of all species on Earth were wiped out, including every non-avian dinosaur. The reign of the giants, which had lasted for over 160 million years, was over in a geological instant. Yet, from this global catastrophe, opportunity emerged. With the dominant reptiles gone, small, scrappy mammals, who could survive on seeds and insects in the dark, found their moment. They diversified and flourished in the empty niches, setting the evolutionary stage that would eventually lead to primates and to us. This collision did not just end an age. It cleared the path for a new one, proving that the most destructive events in the cosmos can also be the most creative forces for change. The death of the dinosaurs was a sudden, violent punctuation mark in Earth's history, but another collision was far slower and more insidious. It was not a rock from space, but a molecule. This is collision number 6, the Great Oxygenation Event, a chemical war that forever changed the air we breathe. For over 2 billion years, Earth's atmosphere was a toxic soup to us, rich in methane and carbon dioxide, but with virtually no free oxygen. Life existed, but it was microscopic and anaerobic, thriving in those poisonous conditions. Then, a new kind of organism evolved, cyanobacteria. These simple microbes possessed a miraculous trick photosynthesis. They could use sunlight, water, and carbon dioxide to produce their own food. Their waste product was oxygen. At first, this oxygen did not accumulate. It was a deadly poison to the existing life. and it quickly reacted with iron dissolved in the ancient oceans. Imagine a world where the seas are green, not blue, saturated with soluble iron. As the cyanobacteria pumped out their oxygen waste, it collided with that iron, causing it to rust. The oceans turned a bloody shade of red as trillions of tons of iron oxide particles settled to the seafloor, forming beautiful layered deposits we call banded iron formations. You can see their striped, rusty evidence in cliffs and mines today, a literal geological record of this global chemical reaction. For millions of years, this process scrubbed the oxygen from the air and water. But the cyanobacteria were relentless. Eventually, they produced oxygen faster than the oceans and rocks could absorb it. The gas began to build up in the atmosphere. To the anaerobic life that had ruled the planet, this was an apocalyptic pollution event. Oxygen was a corrosive, reactive toxin that attacked their very cellular machinery. It triggered the planet's first mass extinction, wiping out vast swaths of the primordial biosphere. Yet from this chemical catastrophe, a new world was forged. The oxygen-rich atmosphere created the ozone layer, shielding life from the sun's harsh ultraviolet rays and allowing it to move onto land. More importantly, oxygen is a powerful fuel for metabolism. It enabled the evolution of larger, more complex, and energetic life forms like us. Every breath you take is a direct result of that ancient, slow-motion collision between biology and geology. A war fought with molecules that set the stage for everything that walks, swims, or flies. While our planet's history is written in chemical and geological collisions, the future of our galaxy is a story of slow, gravitational violence already in motion. Collision number 7 is not a distant possibility. It is a certainty, a cosmic appointment set for 4.5 billion years from now. Our Milky Way and the Andromeda galaxy, currently 2.5 million light-years apart, are on a collision course. Picture this not as a sudden, fiery crash, but as the universe's most majestic and patient dance. For the next several billion years, the mutual gravity of these two spiral giants will pull them closer in a slow, cosmic waltz. As they near, their immense gravitational fields will begin to distort each other. Long, shimmering tidal tails of stars, gas, and dust will be pulled out into the void, like streamers of cosmic taffy stretching across the darkness. The beautiful, orderly spiral arms we see today will warp and tangle. From a hypothetical planet within either galaxy, the night sky would undergo a breathtaking transformation. Andromeda, currently a faint, fuzzy smudge in our northern sky, would grow larger and brighter with each passing million years, eventually filling half the heavens with a swirling disk of alien stars. The crucial thing to remember is this: space is mostly empty. The stars within galaxies are like grains of sand separated by miles of ocean. When the galaxies finally merge, their stars will not smash into each other. They will simply slip past one another, their paths woven together by gravity's invisible hand. After a billion years of this gravitational tug-of-war, the two galaxies will settle into a new, blended form, a giant, football-shaped elliptical galaxy that astronomers have playfully nicknamed Milkomda. Our solar system will likely be flung into a new, wider orbit, but it will probably survive the upheaval. The sun, by then, will be nearing the end of its life, but the night sky for any future inhabitants of Earth will be utterly alien, a testament to the slow, beautiful, and inevitable collisions that continue to reshape the cosmos. The future of our galaxy is written in the skies of the present, if you know where to look. A stunning preview of the Milky Way's fate is currently unfolding 140 million light-years away, in the southern constellation of Corvus. There, two beautiful spiral galaxies, known together as the antennae galaxies, are locked in a spectacularly violent embrace. This is not a slow, distant approach. It is a late-stage merger, a cosmic car crash happening in slow motion over hundreds of millions of years. You can see the evidence in the most famous images of this pair. Two distinct galactic cores, once the hearts of separate spirals, now blaze with newborn stars, surrounded by a chaotic swirl of dust and gas. But the most breathtaking feature are the two long, graceful arcs of stars streaming out in the darkness. These are the tidal tails, gravitational scars pulled from the galaxies as they swung past each other, giving the system its insect-like name. Within those luminous streams, millions of stars have been ripped from their original homes and cast adrift. Yet, this destruction is also an engine of creation. The real story of the antennae galaxies is not just the collision, but what the collision triggers. As the immense clouds of hydrogen gas within the two galaxies slam together, they are violently compressed. Think of it like squeezing a cosmic sponge. This compression creates pockets of incredible density, and gravity takes over. These dense knots collapse, and in a chain reaction of stellar birth, new stars ignite by the millions. Astronomers call this a starburst, a ferocious, galaxy-wide baby boom of stars. The antennae system is one of the nearest and brightest starburst galaxies known, a brilliant, roiling nursery where stars are being forged at a rate hundreds of times faster than in our own quiet Milky Way. This makes it a perfect real-time laboratory. By studying the antennae, we can watch the physics of galactic collisions play out before our telescopes. We see how gravity tangles structure, how gas is funneled to feed black holes, and how the shockwaves of merging galaxies light the fuse for new generations of stars. It is a beautiful, violent blueprint for what will one day happen to our own galactic home. A reminder that the universe is not a static museum, but a dynamic, evolving arena of constant construction and change. The violent beauty of the antennae galaxies shows us how normal matter behaves in a collision. But what about the stuff we cannot see? Our ninth cosmic collision is perhaps the most important piece of forensic evidence ever gathered in astronomy. It is called the Bullet Cluster, and it did not just reveal a collision. It captured a cosmic crime scene, proving the existence of the universe's greatest mystery, dark matter. The Bullet Cluster is actually two enormous galaxy clusters that have recently slammed right through each other. Each cluster contains hundreds of galaxies, but the galaxies themselves are not the main event. They are like swarms of bees flying through a cloud of smoke. The smoke here is the searing hot intergalactic gas that fills the space between the galaxies. This gas is normal matter, and when the two clusters collided, this gas cloud experienced a drag force like air resistance, causing it to slow down and pile up in the center of the collision. Telescopes that see in X-ray light show this clearly, a spectacular bullet-shaped shockwave of superheated gas, glowing at 100 million degrees, stuck in the middle of the aftermath. But the galaxies, those swarms of bees, behaved completely differently. Because space is so empty, they passed right through each other with almost no interaction, continuing on their way. Now, here is where the detective work begins. Scientists used a phenomenon called gravitational lensing to map the total mass of the cluster system. Gravity bends light, so by measuring how the cluster distorts the images of galaxies far behind it, astronomers can create a map of where the mass is concentrated. The result was astonishing. The map of total mass did not line up with the glowing cloud of hot gas. Instead, the bulk of the mass, the gravity that was bending the light, was located right where the galaxies were, far ahead of the lagging gas. This was the proof. The normal matter, the gas we can see with X-rays, had been separated from the source of most of the gravity. Something invisible, making up most of the mass, had kept going with the galaxies. That something is dark matter. This collision demonstrated that dark matter does not interact with light or with normal matter in any significant way, except through gravity. It passed through the chaos unscathed, while the normal gas got caught in the cosmic traffic jam. The bullet cluster is not just a picture of destruction. It is a snapshot of reality being pulled apart, a direct observation that most of what holds the universe together is a ghostly substance we can only detect by the shadow it casts. Dark matter may shape the cosmos invisibly, but the most powerful king in our own solar neighborhood was born from a very different kind of violence. To understand Jupiter, you must travel back to the solar system's infancy, a time of relentless chaos. The disk of gas and dust swirling around our newborn sun was not a peaceful nursery. It was a demolition derby. Countless chunks of rock and ice, called planetesimals, constantly jostled and collided. Through a process of gravitational attraction and sheer chance, the largest of these began to snowball, growing into planetary embryos, protoplanets the size of Mars or even larger. In this crowded, violent arena, collisions were not accidents. They were the primary method of construction. One embryo, orbiting about 5 times farther from the Sun than Earth does, began to win. With every merger, every collision with another massive chunk of material, its core grew. This is the core accretion model. Picture a snowball rolling down a hill, but instead of snow, it is gathering boulders of rock and ice. Through countless impacts over millions of years, this embryo assembled a core dozens of times more massive than the entire Earth. That was the tipping point. Once this solid core reached a critical mass, its gravity became strong enough to do something extraordinary. It began to rapidly pull in and hold onto the lightest elements in the protoplanetary disk, hydrogen and helium gas. The growth switched from a steady accumulation of rock to a runaway feeding frenzy. A gigantic, thick envelope of gas collapsed onto that mighty core, swelling in size at a breathtaking rate. In perhaps only a few million years, it transformed from a large, rocky world into the gas giant we know today. Every one of those ancient, violent collisions was essential. They built the gravitational anchor that allowed Jupiter to claim its crown, becoming the solar system's heavyweight champion, whose gravity still dictates the orbits of asteroids and comets, protecting the inner planets even as its birth cleared the neighborhood through sheer collisional force. Jupiter's violent birth cleared a path, but its neighbor Saturn earned a crown of pure celestial wreckage. The 11th massive cosmic collision gave us the solar system's most breathtaking sight, not by building a world, but by utterly destroying one. Saturn's magnificent rings, those pristine bands of ice and rock, are likely the glittering graveyard of a lost moon. The leading theory is a story of gravitational betrayal. Billions of years after Saturn formed, its system of icy moons was a busy place. One moon, perhaps as large as the planet Mercury, found itself on a dangerously unstable orbit. As it spiraled inward, Saturn's immense gravity began to pull harder on the side of the moon facing the planet than on the far side. This difference in force, called a tidal force, stretched the moon like taffy. Once it crossed an invisible boundary known as the Roche limit, the pull from Saturn became stronger than the gravity holding the moon itself together. The moon did not simply crash, it was methodically shredded. In a catastrophic, slow-motion collision with the planet's own gravity, the icy satellite was torn apart. Its fragments, from mountain-sized boulders to fine dust, were scattered into orbit, where they quickly spread out into the flat, dazzling disk we see today. Some scientists propose alternative origins, like a giant comet being captured and disintegrated, or a violent crash between two pre-existing moons. But the tidal destruction theory fits the evidence beautifully. The rings are almost pure water ice, remarkably bright and clean, suggesting they have not been darkened by billions of years of cosmic dust bombardment. This points to a surprisingly young age, perhaps only 100 million years old, meaning they formed when dinosaurs still walked the Earth, and they are not a static monument. They are a dynamic, ongoing collision scene. Particles within the rings constantly jostle and collide, shepherded by the gravity of tiny shepherd moons. Waves and ripples propagate through them, and material slowly rains down onto Saturn's clouds. We are not looking at ancient frozen architecture. We are witnessing the active, glittering aftermath of a single cataclysmic event. A reminder that even a planet's gravity can be an instrument of sublime destruction. While Saturn's rings are a monument to destruction, a neighboring world may have been permanently broken by it. Venus, our so-called sister planet, is a vision of hell. Its surface is hot enough to melt lead, crushed under an atmosphere 90 times thicker than Earth's, and shrouded in clouds of sulfuric acid. This was not always its fate. Many planetary scientists now suspect that Venus may have started out remarkably Earth-like, with oceans and a temperate climate. Its descent into a furnace might trace back to a series of catastrophic collisions, a planetary trauma from which it never recovered. The hypothesis is chilling. During the late heavy bombardment, while Earth was being seeded with water, Venus may have suffered a different kind of pummeling. Imagine not one, but several colossal, late-arriving impactors, each one far larger than the dinosaur-killing asteroid that struck Earth. The consequences would have been apocalyptic. First, such impacts would have delivered immense amounts of energy directly into the young planet's atmosphere and crust. They could have literally boiled away Venus's early oceans, blasting the water vapor into space or breaking it apart with ultraviolet radiation. Without vast oceans to act as a climate regulator and a sink for carbon dioxide, the planet's thermostat would have broken. Second, and perhaps more crucially, these giant impacts may have fatally wounded Venus's geological heart. On Earth, plate tectonics acts like a planetary recycling system. Our moving crust pulls carbon dioxide from the atmosphere, locking it away in rocks, which are then subducted into the mantle. This process, operating over millions of years, has kept our climate relatively stable. A series of gargantuan impacts on early Venus could have delivered so much heat to its crust that it effectively cooked it, creating a single, thick, stagnant lid of rock. Without the churning motion of plate tectonics, Venus lost its primary mechanism for removing carbon dioxide from the air. The gas began to accumulate. Sunlight penetrated the atmosphere, warming the surface, but the thick blanket of carbon dioxide trapped that heat, preventing it from escaping back into space. This is the runaway greenhouse effect. The planet grew hotter, which baked more carbon dioxide out of the rocks, which trapped more heat, in a vicious, self-perpetuating cycle that ultimately created the scorching pressure cooker we see today. Earth, by contrast, may have been hit just right with impacts large enough to deliver water and stir the mantle to initiate tectonics, but not so many or so violent that they sterilize the planet's geology. It is a stark reminder of how fine the line can be between a living world and a dead one. A few different collisions in the early solar system, and our own blue marble could have become a second twin of hell. Venus shows us a world broken by collisions, but another planet was simply knocked sideways. Uranus, the pale blue ice giant, spins on its side, while every other planet in the solar system rotates like a top. Uranus rolls like a ball. Its axis is tilted a staggering 98 degrees, meaning its poles point almost directly at the sun during their respective summers. For a quarter of its 84-year orbit, one pole basks in perpetual daylight, while the other is locked in an endless, frigid night. This bizarre orientation is not a quirk of formation. It is the signature of a planetary-scale catastrophe, a collision so massive it literally tipped the world over. The leading theory points to a single, shattering impact early in the solar system's history. An object roughly the size of Earth, a protoplanet or massive planetary embryo, is thought to have slammed into a young Uranus. This was not a glancing blow. It was a direct, off-center hit with enough force to reorient the entire planet. The impactor itself would have been absorbed, its material mixing into Uranus's icy mantle and possibly forming a dense, layered core that still affects the planet's internal heat flow today. The collision's violence did not stop with the tilt. It likely explains Uranus's deeply strange magnetic field. Unlike the neatly aligned magnetic fields of Earth or Jupiter, Uranus's field is chaotic, offset from its center, and tilted at a wild 60-degree angle from its already sideways axis. Scientists believe the impact scrambled the planet's internal dynamo, the flow of electrically conductive material deep inside that generates a magnetic field. The crash may have left that dynamo off kilter, creating the lopsided magnetic bubble that surrounds the planet. Even Uranus's family of moons and rings bear the marks of this ancient violence. They orbit neatly around the planet's tilted equator, following the new plane of rotation established by the impact. This suggests they formed from the debris disk that coalesced after the collision, a disk of shattered material that settled into the new equatorial plane. Without that single, defining collision, Uranus would likely be a much more conventional ice giant, with normal seasons and an orderly magnetic field. Instead, it is a perpetual reminder of the chaos of the early solar system, a world forever leaning on its side from a blow delivered over 4 billion years ago. Uranus was knocked sideways by a planetary embryo, but some collisions forged the very atoms that make up our world. The 14th collision on our list is the most extreme alchemy in the universe. It begins with the corpses of massive stars. When a giant star dies in a supernova, if its core is between about 1.4 and 3 times the mass of the Sun, it does not become a black hole. It collapses into a neutron star. Imagine the mass of a mountain compressed into a sphere the size of a city. A single teaspoon of this material would weigh as much as all of humanity. These objects are so dense that protons and electrons are crushed together, forming a sea of pure neutrons. They are cosmic tombstones of incredible gravity and magnetism. Sometimes, 2 of these stellar corpses become trapped in a deadly gravitational embrace. Orbiting each other hundreds of times per second, they spiral inward in a dance that can last for millions of years, slowly losing energy by rippling the fabric of space-time itself. This is the inspiral. In the final moments, they accelerate to a significant fraction of the speed of light before they finally collide. The merger is an event of almost incomprehensible violence. On August 17, 2017, the world's observatories witnessed such an event. Gravitational wave detectors felt the distinctive chirp of two neutron stars spiraling together, and just 1.7 seconds later, space telescopes caught a brilliant flash of gamma rays, a short gamma ray burst, the birth cry of the collision. For days, the aftermath glowed across the electromagnetic spectrum, from X-rays to radio waves, in a brilliant display called a kilonova. But the true magic happened in the heart of that cataclysm. The collision ejected a cloud of material rich in free neutrons at incredible speeds. In this environment of extreme density and energy, a frantic process called rapid neutron capture, or the R process, took place. Atomic nuclei were bombarded by a blizzard of neutrons, building heavier and heavier elements in an instant. This is where the universe forges its heaviest atoms. In that single event, astronomers estimate that the equivalent of several Earth masses of gold and platinum were created and blasted into space, along with other rare elements like uranium and thorium. So the gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers some reactors, these are not ancient relics from the Big Bang. They are stardust, yes, but stardust born in a specific, spectacular kind of violence. They were forged in the final, shattering embrace of two dead stars, billions of years ago, and scattered across the galaxy, eventually finding their way into the cloud that formed our solar system, and finally, into the objects we hold in our hands. The most precious metals on Earth are souvenirs from the most violent collisions in the cosmos. That precious gold forged in a neutron star collision was not created in isolation. It was part of a much larger cycle, a cosmic chain reaction where death directly fuels new life. This brings us to the 15th massive cosmic collision, where the most destructive force in a star's life becomes the ultimate creative spark. A supernova shockwave is not just an explosion. It is a cosmic sledgehammer. When a massive star reaches its end and detonates, it does not simply vanish. It blasts its outer layers into the surrounding space at speeds of tens of thousands of kilometers per second. This expanding shell of superheated gas and debris, carrying all those newly forged heavy elements, races outward for light years. Eventually, this titanic wall of energy can slam into a quiet, cold region of space known as a giant molecular cloud. These clouds are the dark, dusty nurseries of the galaxy, vast collections of hydrogen, gas so cold and dense that they are on the very edge of collapsing to form new stars. They are in a fragile balance, their internal pressure just barely resisting the inward pull of their own gravity. Then the shockwave arrives. Think of it like a sonic boom, but on a stellar scale. The leading edge of the supernova remnant, moving faster than the speed of sound in that cloud, crashes into the cold gas. It compresses it violently, squeezing the cloud in an instant. That delicate balance is shattered. The increased pressure from the collision overcomes the cloud's internal support. Pockets within the cloud become so dense that gravity wins. They begin to collapse inward. In that collapse, a new star is born. Our own sun likely owes its existence to such an event. About 4.6 billion years ago, a shockwave from a nearby supernova, perhaps from one of those first-generation monster stars, plowed into a giant molecular cloud in a quiet spiral arm of the Milky Way. The cloud fragmented, and one of those collapsing knots of gas and dust became our solar system. The evidence is in the rocks. Meteorites, the oldest solid objects we can study, contain tiny, exotic grains of material that could only have formed in the heart of a supernova. We are literally made from the ashes of a dead star, ignited by the force of its final breath. This is the beautiful, paradoxical rhythm of the galaxy. A star's catastrophic death sends a ripple through the cosmos that triggers the birth of its successors, seeding them with the complex chemistry needed for planets and, ultimately, life. The violence is not an end, it is a catalyst, ensuring the story continues. The death of one star can trigger the birth of another, but entire galaxies can be consumed to fuel their own growth. Our own Milky Way is not the pristine spiral we once imagined. It is a galactic cannibal, and its last great feast left a fossil record written in the motions of billions of stars. This discovery came from the European Space Agency's Gaia satellite, a mission tasked with creating an unprecedented three-dimensional map of our galaxy. Gaia did not just measure where stars are, it measured how they move. When scientists analyzed this colossal dataset, they found something astonishing. A huge population of ancient stars, mostly in the galactic halo surrounding the Milky Way's disk, were not moving randomly. They were tracing chaotic, elongated orbits, plunging toward the galactic center and then swinging far out again. Their paths were like a scattered flock of birds caught in a whirlwind. These stars were the survivors of a cataclysm, roughly 10 billion years ago, when the Milky Way was still young and forming. A dwarf galaxy perhaps 1/4 its mass came hurtling in on a doomed trajectory. Astronomers have nicknamed this interloper Gaia Sausage Enceladus, piecing its story together from its stellar remains. The collision was not a clean merger. It was a violent disruption. The smaller galaxy did not survive the encounter intact. The immense gravitational tides of the Milky Way tore it apart, shredding its structure and scattering its stars into those wild, radial orbits we see today. This was not a minor event. It was a defining moment. The influx of so much material, gas, and stars from the doomed dwarf fundamentally reshaped our galaxy. It likely contributed to building the Milky Way's thick disk, the puffy region of older stars above and below the main spiral plane. It also enriched the galactic halo with its ancient stellar population. Perhaps most importantly, the collision would have sent powerful shockwaves through the Milky Way's own gas reservoirs, compressing them and triggering a frenzied burst of new star formation. A starburst that helped build the galaxy we recognize. So when you look up at the band of the Milky Way on a clear, dark night, you are not just seeing our home. You are gazing at the digested remains of a galactic neighbor, a cosmic meal that helped make us what we are. The evidence of that ancient violence is still swirling around us, a ghost in the machine of our galaxy. Our galaxy's ancient feast is still visible in the motions of stars, but its current meal is on full display in the southern hemisphere's night sky. Two fuzzy, cloud-like patches of light, visible far from the city glow, are not clouds at all. They are whole galaxies caught in the act of being dismantled. The large and small Magellanic Clouds are our Milky Way's largest satellite galaxies, and they are currently paying a terrible gravitational price for their proximity. They are not on a collision course to merge with the disk of our galaxy head-on. Instead, they are in a long, looping orbit around us, and with each close pass, the Milky Way's immense gravity exerts a devastating tidal force. Think of it as a cosmic game of tug-of-war. The side of the dwarf galaxy facing the Milky Way feels a stronger pull than the far side. This difference stretches the galaxy, pulling stars and, especially, vast clouds of hydrogen gas away from it. This process has created one of the most spectacular structures in our galactic neighborhood. A structure you cannot see with your naked eye, but which radio telescopes reveal in stunning detail. It is called the Magellanic Stream. Picture a faint, shimmering river of hydrogen gas, over 600,000 light-years long, arcing across nearly half of the southern sky. This river is not connected to the galaxies anymore. It is the debris trail, the cosmic breadcrumbs, left behind as the Magellanic Clouds have swung around our galaxy over billions of years. The gas was stripped away by those relentless tidal forces, a slow motion spill of primordial fuel. This ongoing interaction is not just a spectacle. It is a vital transfer of resources. That hydrogen gas in the Magellanic Stream is eventually falling toward the Milky Way, where it will replenish the raw material for future generations of stars. The dwarf galaxies themselves are being distorted, their shapes warped, their stars slowly being added to our galactic halo. They are being consumed. In perhaps another 2 or 3 billion years, they will be fully absorbed, their identity lost within the greater body of the Milky Way. This is not a catastrophic, fiery crash. It is a slow, inexorable digestion, a demonstration of how even now, our seemingly stable galaxy is actively growing and changing by tearing its smaller neighbors apart. These lonely intergalactic travelers are some of the fastest objects in the galaxy, and they are not propelled by engines. They are cosmic bullets fired by the most powerful slingshot we know. Deep in the heart of the Milky Way, 26,000 light-years from Earth, lies Sagittarius, a star, our galaxy's supermassive black hole. It is a monster with the mass of 4 million suns, and its immediate neighborhood is a chaotic, high-stakes gravitational arena. Stars orbit it at blistering speeds, and some travel in pairs as binary systems. Now, picture one of these binary pairs on a long, looping orbit that takes it perilously close to the black hole's event horizon. The gravitational forces here are so extreme that the very concept of a stable orbit breaks down. As the binary system swings in, the black hole's immense pull does something diabolical. It treats the two stars not as a single unit, but as separate objects. In a process called the Hill's mechanism, the black hole's gravity can rip the binary apart. One star is captured, falling into a tight, doomed orbit around the black hole. The other, in a cosmic act of robbery, steals the orbital energy of its captured partner. It is flung away, slingshotted out of the galactic core at a staggering speed, sometimes over 2 million miles per hour. This is a hypervelocity star. At that velocity, it is not just moving fast. It is moving faster than the galaxy's escape velocity. This star is not on a long orbit. It is on a one-way ticket out of the Milky Way entirely, destined to fly alone through the dark intergalactic voids for eternity. Astronomers have detected several of these runaway stars, their incredible speed betraying their violent origin story. They are the sole survivors of a gravitational encounter with a monster, their trajectories tracing a straight line back to the scene of the crime at the center of our galaxy. Each one is a permanent exile, a blazing testament to the chaotic forces that rule the universe's densest places, where a close pass is not a near miss, but a life sentence of solitary flight. Those hypervelocity stars are permanent exiles, but the outer darkness of our own solar system is filled with silent, frozen exiles of a different kind. Far beyond the orbit of Neptune, extending perhaps halfway to the nearest star, lies a vast, spherical shell of icy debris known as the Oort cloud. It is the solar system's final frontier, a graveyard of primordial material left over from our formation. Here, trillions of icy bodies, some as large as mountains, drift in a deep freeze so profound that a single orbit can take millions of years. They are held by the sun's feeble gravity, but only just. This makes them exquisitely sensitive to any passing gravitational whisper. And in the busy galactic neighborhood, whispers are constant. This brings us to collision number 19, a collision not of objects, but of gravitational fields. As our sun orbits the galaxy, it does not travel alone. Every 26 million years or so, it bobs up and down through the plane of the Milky Way. During this journey, it can pass close to other stars, drift through the fringes of a giant molecular cloud, or simply feel the subtle, stretching pull of the galaxy's overall gravity. Any of these events acts like a gentle but persistent nudge against the delicate balance of the Oort cloud. Think of it as a cosmic hand brushing against a cloud of dandelion seeds. The gravitational influence of a passing star, even light years away, can perturb the orbits of these distant icy bodies. Some get nudged inward onto long, elliptical paths that bring them screaming into the warmth of the inner solar system. We see them then as magnificent long-period comets, with tails that can stretch across the sky. But this gentle gravitational collision has a dark, delayed consequence. A close stellar passage or a trek through a dense patch of the galaxy might not dislodge just one or two comets. It could trigger a comet shower, sending a storm of icy bodies plunging sunward over thousands of years. The inner solar system becomes a shooting gallery. While most comets miss the planets, the sheer increase in traffic raises the odds of a catastrophic impact. A large comet striking Earth would be an event far more devastating than an asteroid impact, potentially triggering a global winter that could last for centuries. Some scientists have looked at Earth's geological record and found evidence of periodic mass extinctions that seem to align roughly with the solar system's galactic bobbing motion. It is a chilling chain of cause and effect. A star we will never see, passing silently in the galactic night tens of thousands of years ago, can give a tiny gravitational push to a chunk of ice in the utter darkness. That ice over millennia falls sunward, grows a glorious tail, and perhaps, just perhaps, sets in motion a chain of events that rewrites the history of life on a planet it has never seen. Our climate, our very existence, can be linked to the gentle gravitational tides of the galaxy itself. The gentle nudges of distant stars can send comets on million-year journeys, but space is also filled with invisible bullets moving at nearly the speed of light. These are cosmic rays, and their existence reveals a universe constantly seething with violence on the smallest scale. Forget asteroids or colliding galaxies. This is about raw subatomic power. Cosmic rays are not rays at all, but particles, mostly lone protons, or the nuclei of atoms like helium or iron, that have been accelerated to unimaginable energies. They are the shrapnel from the universe's most powerful explosions, flung across the galaxy by the magnetic shockwaves of supernova remnants. Think of a supernova's expanding blast wave as a natural, cosmic particle accelerator, more powerful than anything we could ever build on Earth. It grabs these atomic fragments and whips them up to over 99.9% of the speed of light. They travel for millions of years, threading through magnetic fields in the void, until some of them finally reach us. Their journey ends in a flash of light we never see. When one of these ultra-high energy particles strikes the top of Earth's atmosphere, it does not simply zip through. It smashes directly into the nucleus of an air molecule, like a subatomic cue ball breaking a rack. This is a collision of pure energy. The impact shatters both particles, creating a cascade of secondary particles, pions, muons, electrons, and more, that themselves collide with other atoms, creating an ever-widening shower. This particle avalanche, called an air shower, can spread over many square kilometers by the time it reaches the ground. We are completely unaware of it, but thousands of these showers rain down on every square kilometer of our planet every second. You have several of these secondary particles passing through your body as you listen to this. This constant, invisible drizzle is a source of natural background radiation, and it presents a real puzzle for the future of human space exploration. Outside the protective blanket of Earth's atmosphere and magnetic field, astronauts on a mission to Mars would be bombarded by these high-energy particles. They can pass right through spacecraft hulls and human tissue, damaging cells and DNA in ways we are still working to fully understand. Yet, these same collisions might also play a subtle role in our own world. Some scientists theorize that the ions created in air showers could act as seeds for cloud condensation, potentially influencing weather and climate in ways we are only beginning to grasp. From the depths of space to the air we breathe and the future of human travel, the universe's smallest, fastest collisions have a surprisingly large reach. The invisible rain of cosmic rays reminds us that violence permeates every scale. But to see the grandest collisions of all, we must look back in time. One of the most profound images ever taken is not of a single event, but a time capsule of the universe's violent adolescence. The Hubble Space Telescope's ultra-deep field is more than a beautiful picture. It is a core sample drilled into the history of the cosmos. For over 11 days, Hubble stared at a patch of sky seemingly empty to all other telescopes, a region no larger than a grain of sand held at arm's length. What it revealed was a universe teeming with light. 10,000 galaxies, some so distant their light has been traveling for over 13 billion years to reach us, fill that tiny void. But look closely at the galaxies in the farthest reaches of that image, the ones whose light is oldest. They are not the majestic, well-ordered spirals and ellipticals we see in our modern universe. They are small, fragile, and chaotic. Many are nothing more than blobs and clumps of young stars. Others are misshapen, stretched into weird tadpole or chain-like forms. These are not finished galaxies. They are galaxies under construction, caught in the act of violent assembly. This is the visual evidence of a universe where collisions were not rare events, but the primary method of growth. Billions of years ago, the cosmos was far smaller and denser. Galaxies were packed closer together, like commuters in a crowded station, and gravitational encounters were frequent and dramatic. What Hubble captured are the building blocks, the smaller protogalaxies, smashing together and merging. That distorted tadpole shape. It is likely two small galaxies that have just collided, their stars pulled into a long tidal tail. That chain of luminous knots. It could be several clumps caught in a series of mergers, a galactic traffic jam from the dawn of time. Each of those 10,000 points of light tells a story of attraction, collision, and consolidation. We are seeing the universe in its most formative and violent era, a period when today's majestic island universes were being forged in countless crashes. The quiet, structured galaxy we live in is the end product of that ancient chaos, a peace that was hard-won through eons of relentless, creative destruction. Mars is slowly bleeding into space. Its thin, cold atmosphere is not a static feature, but the dwindling remnant of a much thicker blanket, eroded away by an invisible wind. This brings us to a collision that happens not in a single cataclysmic moment, but in a relentless, slow-motion assault spanning billions of years. It is the ongoing impact between the Martian atmosphere and the solar wind. Our sun is not just a source of light and heat. It constantly exhales a supersonic stream of charged particles, protons, and electrons that races outward in all directions. This is the solar wind, and it carries with it the sun's own magnetic field, stretching it across the entire solar system. For a planet like Earth, this cosmic gale is mostly harmless. We are protected by a powerful global magnetic field generated by the churning of molten iron in our core. This magnetic bubble, called the magnetosphere, acts like a shield. When the solar wind hits it, the charged particles are deflected around our planet, flowing harmlessly past like water around a stone in a stream. Mars tells a very different story. Billions of years ago, its internal dynamo, the engine that powered its global magnetic field, shut down. The planet's core cooled and solidified. Its protective shield faded away. Today, Mars has only patchy, localized magnetic fields frozen into its ancient crust. Without a global magnetic umbrella, the Martian atmosphere is completely exposed. The solar wind does not deflect. It strikes the upper atmosphere directly. Think of it less like a wind and more like a sandblaster made of energy. The high-energy particles in the solar wind collide with molecules in Mars's air, primarily carbon dioxide and oxygen. These collisions are so violent they can knock atoms right out of the planet's gravitational grip. It is a process called sputtering. Over eons, this constant, invisible sandblasting has stripped Mars of perhaps the majority of its original atmosphere. Spacecraft like MAVEN have orbited Mars and directly measured this escape, watching as solar storms dramatically increase the rate of atmospheric loss. The consequence of this slow-motion collision is written across the Martian surface. Robbed of its thick atmospheric blanket, Mars could no longer retain heat. Its surface pressure plummeted. Any liquid water on the surface would have either frozen or simply boiled away into thin air, its molecules themselves eventually torn apart by sunlight and carried off by the solar wind. What was likely once a warmer, wetter world, with rivers and maybe even lakes, became the freeze-dried desert we see today. Our blue planet and the red planet started with similar ingredients, but a critical difference, a living magnetic heart, meant one world held onto its air and its oceans, while the other saw its life-giving envelope slowly, silently stolen away by the sun. A silent, invisible bullet crossed the void in June of 1908. It was not a dinosaur killer, but a stark warning. On the morning of June 30th, over a remote forest in Siberia near the Tunguska River, a small asteroid, or perhaps a fragment of a comet, no more than 60 meters across, entered Earth's atmosphere at over 50,000 kilometers per hour. It did not strike the ground. The pressure of plowing through our thick air at such speed was too much. Roughly 8 kilometers above the Earth, the object disintegrated in a colossal explosion, a fireball in the sky with the force of 10 to 15 million tons of TNT. This aerial burst released energy equivalent to a large hydrogen bomb. The effect on the ground was apocalyptic. An immense shockwave of superheated air radiated outward, flattening over 2,000 square kilometers of ancient Siberian forest. 80 million trees were snapped like matchsticks and thrown outward in a radial pattern, their trunks pointing away from the blast epicenter. The roar was deafening, and the seismic vibrations were recorded on instruments as far away as England. For days afterward, the atmosphere across Europe and Asia was filled with fine dust, scattering sunlight and creating luminous, silver-blue night skies so bright that people in London could reportedly read newspapers at midnight. The event was so remote that for years, the outside world knew little of it. When expeditions finally reached the site, they found no crater. They found only a vast, eerie landscape of felled and charred trees, a silent testament to a blow that never quite landed. Tunguska is our clearest modern example of a significant cosmic impact. Had it occurred just a few hours later, The rotation of the Earth would have placed a major city directly in its path, and the devastation would have been incomprehensible. It serves as a powerful, sobering reminder that the cosmic shooting gallery is not a relic of the distant past. The clock is always ticking. Objects of this size are estimated to strike Earth every few hundred years. This reality is why astronomers now scan the skies with programs like Pan-STARRS and the upcoming Vera C. Rubin Observatory, cataloging near-Earth objects to predict potential threats decades or even centuries in advance. It is also why missions like NASA DART experiment, which successfully nudged a small asteroid's orbit, are not just science projects. They are the first tentative steps in learning how to defend our planet, turning the page from passive observation to active planetary defense. The forest at Tunguska still bears the scars, a quiet lesson written in fallen wood about the necessity of looking up. Tunguska reminds us to watch the skies, but the most important collision we can observe is not a threat. It is a whisper from the beginning of everything. To find it, we must journey back to a time when the universe was not dark, but blindingly bright. 380,000 years after the Big Bang, the cosmos was a seething, opaque fog. It was a plasma, a soup of fundamental particles so hot that electrons and protons could not hold together. They were constantly being ripped apart by the intense radiation, a perpetual, chaotic collision that scattered light at every turn. A photon, a particle of light, could not travel more than a tiny fraction of an inch before slamming into a free electron and being sent careening in another direction. The universe was a glowing, impenetrable murk. Then a profound change began. The relentless expansion of space was doing its work, stretching the fabric of reality and cooling it down. The temperature finally dropped below a critical threshold, about 300 degrees Celsius. In that moment, the universe crossed a line. Electrons, moving slowly enough now, could finally be captured by the atomic nuclei they had been fleeing. They collided with protons and settled into stable orbits, forming the first atoms of neutral hydrogen. This event is called recombination, though it was really the first combination. It was a cosmic calm after the storm. As the fog of free electrons cleared, something miraculous happened. The photons, which had been trapped in the constant scrum, were suddenly set free. For the first time, they could travel in straight lines without constant interruption. The universe became transparent. This moment of liberation is known as the epoch of last scattering. The light that was released at that instant has been traveling ever since, for over 13.8 billion years, carrying with it a perfect imprint of the infant cosmos. We detect that light today not as visible light, but stretched and cooled by the expansion of the universe into the faint microwave hum we call the cosmic microwave background. It is the oldest picture we have, a baby photo of reality when it was only 0.003% of its current age. That faint, uniform glow you see on static-filled old television sets. About 1% of that snow is this ancient light, the afterglow of creation itself. This collision of particles into atoms did more than just clear the fog. It gave us our single most important tool for understanding the universe. By mapping the tiny, 1 part in 100,000 temperature fluctuations in this background radiation, cosmologists can read the blueprints of the early universe. Those minute ripples are the seeds of all future structure, the gravitational wells that would one day pull matter together to form galaxies, stars, and us. The cosmic microwave background is the ultimate forensic evidence, a snapshot of the moment the universe became a place where light, and eventually eyes to see it, could exist. That ancient whisper of creation tells us how it all began. But what of the end? Our final collision is not a memory or even a prediction. It is a thought experiment on the scale of eternity. Picture a universe grown impossibly old, trillions upon trillions of years from now. The stars have all burned out. The galaxies have merged into monstrous, dark ellipsoids, their lights extinguished. The cosmos is a vast, frigid graveyard, expanding into an endless, silent night. Yet, even in this profound darkness, one last form of activity remains. At the heart of each of these dead galactic husks, a supermassive black hole still waits. They are the final monuments, the ultimate survivors of a universe that has run its course. And gravity is patient. Over timescales that make the age of our universe seem like a single heartbeat, these leviathans will begin a final, slow dance. As space continues its relentless expansion, these merged galaxy clusters will become the last islands of structure. The black holes within them will be drawn together by their own immense gravity, a process so slow it defies human comprehension. They will spiral inward, not through a crowded sky of stars, but through an absolute void darker than any we can conceive. Their inspiral will be silent, invisible, and achingly gradual, measured not in years, but in epochs longer than the current lifetime of every star that has ever shone. When they finally merge, the event will be one of unimaginable violence in a universe of utter stillness. Ripples in space-time, gravitational waves, will be the only testament. These waves will carry away the last great bursts of energy in a cosmos that has otherwise achieved a state of maximum entropy, a uniform, cold equilibrium often called the heat death. There will be no one to witness it. No new stars will be ignited from the debris, for there is no debris left. No new elements will be forged. The collision will simply be the last flicker of organized structure surrendering to the dark. It brings our journey full circle, from a single point of infinite energy and density exploding into being, to the last massive objects slowly coalescing and vanishing into the quiet hum of an eternal expansion. The universe may have begun with a collision of energy birthing everything, and it may well end with the collisions of darkness, signaling a final, profound silence. From a single point of infinite potential to the final black holes, merging in a dark, cold void, every chapter of our cosmic story has been written by collisions. They are not random acts of destruction, but the fundamental, creative force of the universe. The Big Bang forged reality itself in a fireball of expansion. Supernova and neutron star mergers cooked the heavy elements that make up our world and our bodies. Galactic cannibalism built the Milky Way, and a rogue planet tipped Uranus on its side. An asteroid cleared the way for mammals, and the gentle gravitational nudges of passing stars still send comets our way. Even the air you breathe is the product of a slow chemical war waged by ancient microbes. Without violence, there is no creation. Without collisions, there is no change. The cosmos is not a static museum piece. It is a dynamic, evolving, and often violent workshop, and every single thing you see is a product of its relentless work. So the next time you gaze at the night sky, remember this. The serene face of the moon is the scar of an ancient impact that gave us tides and stable seasons. The gold in a ring or a microchip was forged in the final, shattering embrace of two dead stars billions of years ago. You are literally made of stardust, assembled by gravity and shaped by cataclysm. We live in a universe of breathtaking beauty born from unimaginable violence, and understanding that story only deepens the wonder. If you enjoyed this journey through the collisions that shaped everything, Be sure to subscribe for more explorations into the mysteries of the cosmos. Let us know in the comments which of these massive cosmic collisions surprised or fascinated you the most. Until next time, keep